So we know now how to put the appropriate number of bonds around the central atom in a Lewis dot structure, but what's actually determining the shape of the molecule? And that is all of the electron groups around the central atom. Electron groups have a lot of names. All they describe is the region of space that electrons occupy. It's not by the number of bonds, it's just by the space. And so these electron groups are sometimes, depending upon the text you look in, called charge clouds. Or electron domains. Sometimes they'll be called regions of electron density. All of these things mean the same. And the thing about them is that they're all negatively charged, as electrons are negatively charged, so they repel each other. The thing that determines the shape of a molecule is how these charge clouds are repelling each other. The fact that they arrange themselves as far away from each other as they could possibly be. So when we're talking about charge clouds in general, charge cloud is a general term. So a lone pair is one charge cloud. It is one region of space that contains electrons. A single bond, a double bond, or a triple bond, all of them count as only one charge cloud. Again, it's just about the region of space. So if you take charge clouds in general, no matter what type of charge cloud they are, and arrange them appropriately in 3D space around the central atom, then that will determine the angle between them. The angle between them will depend upon how many charge clouds there are. So if you have two charge clouds, for example, as far away from each other as they could be is on the opposite side of each other, giving a 180-degree angle. Three charge clouds, the farthest away from each other they could be is 120 degrees. And for four charge clouds, it's challenging to think of in 3D space, but that's 109.5 degrees, called a tetrahedral. So molecular geometry is only different from electron geometry in that we're only talking about bonds. We're only talking about the bond angles. Not the angles between all charge clouds. You need to remember, though, that the electron geometry determines what the bond angles are. And then the molecular geometry just reports that angle. So let's compare a couple of molecules. So we have CH4. Let's draw that out. C in the middle. Four hydrogens. And so it's got four electron groups. So our electron geometry is tetrahedral. All of those groups are bonds. There are no lone pairs. They are bonds. So my molecular geometry is also tetrahedral. Let's look at NH3, however. We've got three hydrogens and a lone pair. So the nitrogen still has four electron groups, four charge clouds. So its electron geometry is the same as the CH4. However, the molecular geometry, because only 3 of those electron groups are bonded electron groups, the molecular geometry is trigonal pyramid. There is a chart in your lab manual that will give you all of the names of the different electron geometries and how they relate to molecular geometries, as well as what the bond angles are for those geometries. Another thing to understand is that not all charge clouds repel with the same strength. Charge density determines the strength of the repulsions. So charge density is the amount of charge over the volume of space. Just like mass density is mass over volume, charge density is charge over volume. So the smaller that charge cloud, the more charge dense it is. So a lone pair contains 2 electrons and is super tiny. It is far more charge dense than any type of bond, single, double, or triple. Those bonds are stretched out. Right, so what that causes is bond angle distortion. Okay, with different charge clouds have different charge densities. Let's look at an example. Let's only look at CH4 and H2O because those have the same electron geometry. CH4, we've got our C in the middle, our H's around. Just like on the previous page, it's the molecular geometry and the electron geometry are tetrahedral. And all of these bonds are the same. They're all equivalent, so they're all pushing on each other. They're all repelling each other equally. And so all of these bond angles are equally 109.5 degrees. Let's look at water, however, H2O. I've got 2 lone pairs on that oxygen. And so my electron geometry, since I do have 4 electron groups around the central atom, my electron geometry is tetrahedral. But my molecular geometry is bent. That's how it looks if I only look at the bonds. And so this angle, because these lone pairs are more charge dense than these bonds, those push the bonds away and thus closer together. So this is going to be a smaller angle of 104.5 degrees.